Polynomial functions, section 3.3 to 3.4. Sketch the graph of f of x equal x minus 1 quantity squared times the quantity x plus 1. Okay, so with the polynomials we'll be working with, it's going to be helpful to get the x-intercepts. And to do that, we want to set f of x equals 0 and solve for x. So we set x minus 1 quantity squared times the quantity x plus 1 equals 0. And we can use the zero product rule. That means either x minus 1 equals 0 or x plus 1 equals 0. Add 1 to both sides, we get x equal 1. Subtract 1 from both sides, we get x equal negative 1. So we have two x-intercepts here. One thing to notice here is that this x-intercept of 1 has multiplicity 2. This is that came from this factor here, which is to the second power. So that has multiplicity 2. The x equal negative 1 has multiplicity 1. This is x plus 1 to the first power. It came from that factor. So it has multiplicity 1. And if a x-intercept has even multiplicity, this multiplicity 2 is even multiplicity, then the graph will touch but not cross at that point. Whereas if the 0 has odd multiplicity, x equal negative 1 has odd multiplicity, then the graph will cross the x-axis at that point. Okay, so then we can plot some points and sketch the graph. I like to pick points on either side of the x-intercepts. I circled the two x-intercepts here, negative 1, 0, and 1, 0. And I like to pick points on either side and then connect the dots. And you'll notice here we have two humps. There's a hump here and a hump there. And in general, polynomials of degree 3 will have up to 2 humps. Sometimes they'll flatten out a little bit, but they'll have up to 2 humps. And they also have up to 3 x-intercepts. In this case, we only have 2 x-intercepts. Okay, so that's the graph of that function. Another example, sketch the graph of f of x equal x to the fourth minus 13x squared plus 36. And this is quadratic in form. So we want to write it like a quadratic equation and solve it like a quadratic equation. We can write quadratic equation, the highest power of x is to the second power. So we want to write x to the fourth as x squared squared, and then minus 13x squared plus 36. And then we can do a substitution, replace u by x squared. Replace x squared with u. So instead of x squared squared, we'll have u squared. Instead of 13 times x squared, we'll have 13 times u, and copy the plus 36. And now it looks like a quadratic equation, and we can solve it like a quadratic equation. I like to try factoring first, and if that doesn't work, I use the quadratic formula. So u times u will give us u squared. Then we need two numbers to multiply to 36 and add up to negative 13. And what works is negative 4 times negative 9. Negative 4 plus negative 9 is negative 13. Negative 4 times negative 9 is 36. And you can check that with the FOIL method. Okay, so now we have a product equal to 0. That means one of the factors has to be 0. So either u minus 4 equals 0 or u minus 9 equals 0. Add 4 to both sides, we get u equal 4. Add 9 to both sides, we get u equal 9. Now we want to substitute back, replace u with x squared. So instead of u equal 4, we'll have x squared equal 4. Instead of u equal 9, we'll have x squared equal 9. And then to solve for x, we want to take the square root, and we get x equal plus or minus 2, or x equal plus or minus 3. Another thing to notice about this function is that it's an even function. We have only even powers of x. For polynomials, if you have only even powers of x, it'll be an even function. And there's a couple implications. One thing is that when you graph it, the left side is going to be the mirror image of the right side. And also, if you compute, for example, 17, f of 17, you're going to get the same answer as f of minus 17. Or if you do f of 4, you'll give the same answer as f of minus 4. So you don't have to do all the computations twice. Okay, so I made a table of values. And I circled the x-intercepts here. We have plus or minus 3, 0, and plus or minus 2, 0. And we want to pick points in between. So I picked plus or minus 4, plus or minus 2.5, plus or minus 1, and 0. And then I computed f of x for each of these. And again, because it's an even function, putting in 4 gives us the same answer as putting in negative 4. This is for, it was not convenient to plot 84. 84 is pretty far up, but so for that one, I just made the graph continue like it indicated by drew the graph to the edge of the graph, going straight up, because it goes up pretty quickly at that point. Okay, so we notice there's 3 humps here. We have 2 humps here at the bottom and 1 hump here, and so that's our graph. And again, polynomials of degree 4 have up to 3 humps, and we do have 3 humps here, and they have up to 4 x-intercepts. Here we have 4 x-intercepts. Okay. Okay, another example, f of x equal 2x cubed minus x squared minus 8x plus 4. And we can, when you have 4 terms, sometimes you can factor by grouping. So we want to group the first 2 terms together and group the last 2 terms together. The first 2 terms have a common factor of x squared, and if we divide, we get 2x minus 1. The last 2 terms have a common factor of negative 4, and if you divide, you get 2x minus 1. And now we have 2 groups. Each group has a factor of 2x minus 1, so that's our common factor. Divide each group by the common factor, the common factors will cancel, and what's left is x squared minus 4. So now we can use the zero product rule. Either x squared minus 4 equals 0 or 2x minus 1 equals 0. Add 4 to both sides, we get x squared equal 4. Add 1 to both sides, we get 2x equal 1. Take the square root, we get x equal plus or minus 2. Divide by 2, we get x equal a half. So we have 3 x-intercepts here, x equal plus or minus 2 or x equal 1/2. And now we can make a table of values and plot the points. Again, I like to pick points on either side of the x-intercepts. So we have an x-intercept here at negative 2, 0, 1/2, 0, and 2, 0. And then pick points on either sides of those, compute f of x, connect the dots. Polynomials of degree, so we have 3 x-intercepts here. We have 2 humps. We have a hump here and a hump down here. And again, polynomials of degree 3 have up to 2 humps and up to 3 x-intercepts. Okay. Another example, f of x equal 2x cubed minus 4x squared, or 2x cubed plus 4x squared minus 2x. And again, we want to solve f of x equals 0 to get the x-intercepts. And because there's a common factor of 2x, we start out by factoring out the common factor. You always want to do that first. If there is a common factor, factor that out first, or generally you want to do that first. So if you divide each term by the common factor of 2x, what's left is 1x squared plus 2x minus 1 equals 0. And then if we solve, we use the zero product rule. So that means either 2x equals 0 or 1x squared plus 2x minus 1 equals 0. Divide by 2, we get x equals 0 or 1x squared plus 2x minus 1 equals 0. Now this equation is going to be difficult to factor, so I'll use the quadratic formula for this. And so plugging into the quadratic formula, x is equal to negative b plus or minus square root of b squared minus 4ac over 2a. And then replacing the letters with the numbers, b is going to be 2, so this is minus 2 plus or minus, and square root, and b squared is 2 squared. 4 times a times c, so it'll be 4 times 1 times negative 1. And on the denominator we have 2 times a, which is 2 times 1. Okay, so 2 squared is 4. Negative 4 times negative 1 is 4. 2 times 1 is 2. And 4 plus 4 is the same as 4 times 2. And as long as there's not more than one minus sign, the square root of a product is the product of the square root. So we can write this square root of 4 times square root of 2. Square root of 4 is 2. And then we can distribute the denominator. Negative 2 over 2 plus or minus 2 root 2 over 2. Negative 2 divided by 2 is negative 1. And the second term, the 2's cancel, and just leaves us with plus or minus root 2. By trial and error, we can approximate root 2 is 1.4. So we'll have negative 1 minus 1.4, which is negative 2.4, or negative 1 plus 1.4, which is positive 0.4. And then we can make a table of values and plot the points. So again, we want to pick points between the x-intercepts and compute f of x for those values, and then plot the points and sketch the graph. So again, this is degree 3. We have up to 2 humps and up to 3 intercepts. And in fact, we do have 2 humps. We have a hump here and a hump down here, and we have 1, 2, 3 x-intercepts. And that concludes this presentation.